Okay, welcome to the third lesson of chapter 3. In lesson 3 and lesson 4 for this chapter, they're both focusing on optimization problems. So just a little bit of an introduction to optimization here. It says, in business, companies often want to find the best or the optimal solution. This often involves finding the minimum, like the minimum cost or the minimum amount of materials or transportation distance, employee hours, etc. Or they want to find the maximum, like maybe they want to maximize their profit, their revenue, maybe they want to maximize the number of items that their factory could produce, that kind of thing. So by modeling situations with an equation, we can find the maximum or the minimum, and this process is called optimization. A lot of times when you hear that someone's like a business analyst or something like that, usually they would use some optimization math in that process. In lesson 3.2, we solved optimization problems when we were given the equation. In these two lessons, we're going to look at optimization problems where you actually have to create the equation. So it's the same algorithm that we were using in the second lesson. It's just that now we have some steps we need to do beforehand. The first thing you need to do is understand the problem. So you're going to draw a diagram, label the given quantities on the diagram, create variables for the unknown quantities. So that's something that we always want to remember to do. Those let X represent blah, blah, blah for each problem. Then you need to create a function in one variable. So sometimes what we start out with is multiple equations, and then we sub one into the other until we get just one function with one variable that's unknown. So kind of like a Y variable and an X variable, but you might start out with many. Then you're going to find the domain, because now you're not going to be given those endpoints that we were given in lesson 2. Now you have to come up with the endpoints. So sometimes you're going to find that x0 is one of the endpoints, especially if I'm talking about measurements, then I can't have a negative side length. And often when time is involved in the problem, you can't have a negative time, but not always. And then after you do this, so let statements, come up with the equation, come up with the domain of the function, then you're going to go through our algorithm from the last lesson. So we're finding the derivative. To find the maxes and minimums, we set the derivative equal to 0, solve for x, then find those y values and the y values at the endpoints. Compare those y values to find the smallest or the largest, depending on what the problem's asking for. Okay, so our first question here, we've got Farmer Frank. So in our first lesson, the type of questions that we're looking at are measurement questions. So things like maximizing or minimizing area, maximizing, minimizing volume, or surface area. So sometimes you have to dig up one of these old formulas. And if it isn't like a basic one, so on the test, I would expect you to like know the area of a rectangle is length times width. Or the volume of a rectangular prism, length times width times height. But anything that gets a little more complicated, I would give you the basic formulas from like your grade 9 formula sheet. All right, so we've got Farmer Frank. He's got 200 meters of fencing, and he's going to build a rectangular enclosure for his llamas and his emus. But they don't get along, so he has to separate the pens. So what that's saying is that I'm going to have a side length on the outside, but I also have to have a length of fencing in the middle to separate the two animals. One side of this enclosure is going to be a stream, and they're all afraid of water, so I don't need to put a fence along that side. I just need to fence the side parallel to the stream. So we're going to determine the dimensions of the fenced field in which the maximum area is enclosed. So what you want to look for when you're doing these questions is, what are you trying to maximize? So here I'm trying to maximize the area. So that's the thing I need an equation for. So I'm looking for an equation for the area. But I need to get that equation down to just one unknown. So it can't be like area equals length times width, because that would be two variables, length and width. I need to get it down to one. But I'm going to use that idea along the way. So before you get started, sometimes it helps to kind of go through like, well, what information am I given here? And here, the only information really that I have other than this lovely diagram that helps me sort out my thoughts is this here of the 200 meters of fencing. And we can kind of think of that as like a perimeter, because fence goes around the outside, but like not technically here, because it's going to also include this middle line. So I'm given that the perimeter is equal to 200 meters. And in this problem, I'm going to be using common variables. So you're noticing that I'm not using a let statement here. Capital P means perimeter. If you want to use capital P to mean something else, then you need to define it as such. But we're using it as perimeter here. Because that's the standard definition. Same thing for lowercase w and lowercase l. They have meanings, width and length. So I'm going to be using that. Now the only thing is you have to define for me on the picture, what are you defining as the width? So I'm going to call this distance here the width. So I'm adding it to my picture, and this is kind of me defining it. So there's a width there, a width here, and another width here. Now there's two different ways to define the length in this problem. You could either say the length is the entire horizontal distance here, or you could try to separate it. Now be careful with separating it because we don't know that the llamas and the emus have the exact same amount of space. We don't know where this line in the middle is. It could be more to the left or more to the right. So just to be safe, I'm going to say that the length here goes all the way across. All right, so I've got that the perimeter is equal to 200 meters. When you have this type of equation or this type of problem, often you're going to use two different equations to create the one that you're looking for. I know that my goal here is to come up with, so I'm just going to write this off to the side because I'm going to do some work under here. My goal here is to come up with an equation for the area of this enclosure. And I can see here that the area, this is just a rectangle, and the area of a rectangle is length times width. But the problem here is I have two variables, so I have to get rid of one or the other. And I'm going to use the perimeter to help me with that. So I can see here that the amount of fencing is going to involve 3 W's and 1 L. So I know that 3 W's and 1 L is equal to 200 meters. And I'm going to use this expression. I'm going to sub it in over here to get rid of either the L or the W. Now, because I don't have a coefficient on the L, it's easier for me to solve for L. Oops. And so I'm going to use this expression. I'm going to sub it in over here. So now I have that the area is equal to, the length is now 200 minus 3W times W. And what I have now is area in terms of the width. So I've made it a function, and that's what I was looking for. So if you were looking back up at our kind of set of steps here, we've got our variables, we've labeled them on the diagram to show how I'm interpreting width and length. We've created a function in one variable at this point, and we used multiple equations, and we subbed one of them into the other to come up with it. So next up, I need to find the domain of this function. So I'm going to come back over here and do some work with this guy because I know that in the next step of my algorithm, I'm going to find the derivative of this. So I'm coming back to that later. Right now, I'm going to think about the domain. And so instead of goal here, you might write like equation or function, maybe makes more sense. All right, so for the domain here, we need the domain, our variable is W now, right? We've got it down to just W, so we need to think about, well, what's the smallest W that we can come up with and what's the biggest W? So when I'm dealing with side measurements, the smallest W is going to be that it has to be bigger than 0, right? So I know that my W has to be greater than or equal to 0. And then I'm going to think about, well, what would be the largest W? And so to do that, what you can do is think about, well, what was the other variable and what kind of is the limitation on that one? So when I think about the largest W is going to come from building with the smallest length. And my smallest L is going to be when L is greater than or equal to 0. So that's going to be my lowest. And then I know that here that L is just 200 minus those 3 W's. And so then I can solve here. Be careful when you're solving an inequality with a negative coefficient. The safest thing to do is add the w over until it's positive, and then you can divide out that coefficient of 3. If you were to move the 200 over, don't forget that when you divide an inequality by a negative, that you need to flip the inequality sign here. So what I've got now is my domain. I'm going to just write it all together like I would normally write a domain. I've got that 0, or that w is sandwiched between 0 and 200 thirds. All right, so we've got our domain, we've got our function. Now we're moving into the actual algorithm that we used in lesson 2. And that algorithm says start by finding the derivative. Now when I look at this, I've got a product rule here. I've got something with w's times something with w's. If you want, you can expand this out. So I'm just multiplying the w into the brackets here, and it becomes quite a bit easier to take the derivative of. And now that I have that, the next step in my algorithm says to set the derivative equal to 0, because we're looking for local maximums and minimums. Where is the tangent line horizontal? And then this is just a linear function, so I can just rearrange to solve. And then in lowest terms, that would be 100 over 3. Okay, so now I am thinking about my algorithm still. I do want to see you going through that algorithm, even though sometimes our problems, we're still at the stage where our problems can sometimes be quite simple in high school. So you may recognize this problem from grade 11 math, actually. We did lots of fencing questions like this, and there are other strategies you could use. In fact, you could even just use grade 10 math and draw this parabola here, be thinking about the x-intercepts, and then you can average the x-intercepts to find the vertex, right? So this is not the only way to do this problem, but I want to see your calculus work here. So the calculus work does involve checking all of my y values in the original function. So this is the function that I came up with, right? This is the function that we care about, that we are maximizing or minimizing. So this is the one that I'm going to plug my endpoints and my my solution here, 100 thirds, into. Now, a lot of times your endpoints are kind of trivial points here. If I plug in w equals 0 into my equation here, either version you can look at, I'm going to get 0. And when I plug 200 thirds in, well, we came up with that number because it makes this length section here equal to 0. So when I plug 200 thirds in here, this first bracket is 0, and then 0 times 200 thirds is still 0. So I still want to see this work, even though it's kind of trivial. And then more importantly, we'll check this guy here. So this is the solution we had. And again, you can sub it into either version of your formula. So here I'm going to pick the second version, but it does not matter. And when I calculate this all out here, I get 10,000 thirds, which, because we're dealing with a measurement problem here, we'll convert that to a decimal. Now the question actually asks me to determine the dimensions of the fenced field. And dimensions are the length and the width. So I need to figure out the length and the width that give me those that maximum area. So we found our maximum area. Here it is. I've got the width already. It's 100 thirds. I just have to find the length. So we know that the length is equal to 200 minus 3w. So the length is going to be 200 minus 3 times 100 thirds, and that comes out to 100. And then we'll just write our sentence about Farmer Frank. And again, you can change this width because we're talking about a measurement problem. And don't forget that the area units are squared. All right, our next question is about building a box out of a piece of cardboard. And in this example, we have a square piece of cardboard, but the same type of problem could have a rectangular piece of cardboard, and you're going to see that in your homework. So we've got this square piece of cardboard. We're going to make an open-topped box by cutting out congruent squares from each corner and folding up the remaining sides. We're going to find the dimensions that will yield the box with the maximum volume. So remember, look for that. What are you maximizing or minimizing? That's the thing you need an equation for. So you're kind of thinking about this, right? The goal here is to come up with V equals some stuff. So the first thing that I might do here in this problem is draw a picture of the information, what we have here. So I've got a square piece of cardboard, and we're going to cut congruent squares from each corner. So I'm actually going to cut like a little square away from here, and I'm going to cut the same square from each corner. I don't know how big that square is yet, but it's going to be the same. Congruent just means the same square from each corner, same size. So imagine this, what you're left with after you cut away those squares, what you're going to do, you're going to have like this flap hanging off to the side here. You're going to fold along this dotted line and then do the same thing with all the flaps on each corner, on each side. So this flap here will fold up and become one of the sides of the box. Same with here and here. All right, so for this problem here, I'm going to come up with some variables here. I'm going to label this just because it might not be obvious, but the height of the box is going to be the side length of these squares. So the height is actually here, this side length of this flap that's left over, right? And some people might use X there, but we'll use H for height. Okay, so we know again that our goal, I've got my variable, I'm going to try and get it down to just using this variable here. I know though that the volume of a rectangular prism or a volume of a box is the length times the width times the height. So remember, my goal is to get rid of the three variables and just get it down to one. So we're going to try to do that here. Now, the length and the width are actually the same in my diagram, right? The length and the width, because it's a square, here's my length, and here's my width, they're the same. Remember that the whole sheet of plastic cardboard was 12 centimeters. So this entire distance here is 12 inches, but we cut away a length of H on this side and a length of H on this side. So the resulting width in here is the original 12 inches minus 2 H's because we cut them off from each corner. And that's going to be the same for the length here. It was 12 all the way across the top here, but we cut off an H on each side. So this one as well is going to be 12 minus 2H to go across. So I'm going to just fill that into my formula, and I'm going to be left with all H variables. So the volume in terms of the height is 12 minus 2H, the length, times 12 minus 2H, the width, times H, the height. And so now we've got our equation of volume in terms of one variable. So we're happy with that. We also need, though, the domain. So when I'm coming up with the domain, I want to be thinking about what's the biggest and what's the smallest that my variable can be. So the smallest H that I'm going to get is going to be H equals 0, so that's going to be my lower bound. And then I have to think about, well, what's the biggest square I could cut out of this sheet of cardboard? And so you're kind of imagining like this square growing out of here, and like it doesn't make sense that the square could be this big because I have to cut a square from both sides, right? So in order for this to work out, I would have to cut this square so that I could duplicate it on the bottom. So I don't want to run out of space there. And so that means that the longest square I can get would be 6 inches, so that the other square I cut from the other side would also be 6 inches. So it's going to be the length of the material divided in half, because I have to cut 2 squares. So it's 6. Now, if the question instead of being a square had been a rectangle, so say one side was 20 and one side was 12, I would still use the 12 because it's the smaller side. Yes, I could cut a bigger side from the 20, but I need to be able to cut the square from the shortest side. So I always use the shorter measurement here on top. And so I've got my domain. It's going from 0 to 6. All right, so we're going to go back. Now we've got our variables, we've got our equation, we've got our domain. This is the function that we are going to try to maximize. And so I'm going to take the derivative of this thing. So you can either expand this first, or you can do, we have a triple product rule here. I'm going to expand it. I think that's what most of you would do. And so I do 12 times 12, I get 144. And then I'm going to do 12 times negative 2, that gives me negative 24. But I also get negative 2 times 12 here, which gives me another negative 24. And together that's negative 48 h's. And then negative 2 times negative 2 gives me positive 4h squared. But I still have that other extra h, so now I'll expand that into the bracket. Moving on to the derivative. That's going to be 96. And you can reorganize this if you want to have that leading, because we're used to that, right? The leading coefficient coming first. Now, after we have the derivative, we want to figure out, well, where does this thing equal 0? So I do have to factor this guy. So I see here that I can take out a common factor of 12. And when I do this, I am going to reorganize. So dividing the 12 out of here first, I get h squared. And then dividing the 12 out of the negative 96, I get negative 8. And then dividing the 12 out of 144, I get 12. And now I'm going to look for two numbers that multiply together to give me 12 and add to give me negative 8. And now I've got it factored and equal to 0, so I'm going to set each bracket equal to 0. But we're not done yet. We have to check those y values. So I'm just working across my page here, checking the y values. Again, I have to check the endpoints even if they seem sort of trivial. So I'm plugging them into my original function, or you can use one of the expanded versions if you like that better. When I plug in 0, I'm going to get 0 times these two values, but that's just going to be 0. When I plug in 6, it's going to make this first bracket equal 0. So I'm going to have 0 times 0 times 6. That also equals 0. And then we'll plug in these two values here. They are both in the interval. Don't forget to check for that. So I've got h equals 2. I've already checked h equals 6. I don't need to check it twice. So just checking h equals 2. And so I'm going to get 12 minus 4 times 12 minus 4 times 2. And that comes out to 128. And so that is, I'm trying to maximize, remember, I'm trying to maximize the volume. So there's my maximum volume, and there's the height or the size of the squares that I'm going to cut. It did ask for all the dimensions though, so I am going to figure out the length and the width. So if the height equals 2, the length is equal to the width, which is equal to 12 minus 4, which is 8. So therefore, All right, I'm going to pause the video there and I'll come back for that last problem, the distance problem.